Good afternoon. Welcome to this talk. My name is Mark Fussell. I'm a program manager that works on the Azure Service Fabric team.
Hi, I'm Vipul Modi. I'm one of the engineering managers on the Service Fabric team.
And so today we're going to talk to you about how you can build scalable, resilient services using the program model APIs. At the end of this talk, we'll encourage you to download an SDK that we shipped this week and use that SDK, and you'll see at the end of this talk, you'll be able to build yourself the same scalable applications we'll show with plenty of demos here today. I'm going to touch a little bit on the benefits of why we built Service Fabric as a platform. We're going to spend the vast majority of our time looking about how we build those applications and those services inside Visual Studio and show you code. And we show you the various programming models we have. And at the end, we're going to take those applications and we're going to show how you can simply scale them all out. If any of you attended Gopal Kakivaya's talk yesterday, he gave a great rundown of why we built a platform for building services that we run at Microsoft. Here in Azure, we've always been focused on building a platform itself. You know, when we first released Azure, we focused a lot on building this concept of worker roles and web roles, because we realized that building on raw VMs is just hard. You know, you can't just build on raw VMs. You know, if a machine fails, what was running on it? How do I fail it all over? How do I recover my service? So as you build services, you need a platform to take that hard work away from you. And we at Microsoft have been doing exactly the same transition for a number of years. We've taken a lot of box products that we built before, SQL Azure, System Center, Link, or Skype for Business, and we've been hosting them as services in the cloud. And we realized when we did that, we had to build a new platform. And we're thrilled to be able to say that after many, many years of development, we've actually kind of get this platform into your hands. Think of this as the next generation of PaaS as a platform that we're giving you, that we use to build and run our own services on. And there's reasons why we had to do this. And the most important thing that came across as we built these services, we realized we had to break down these applications into the concept of microservices, pieces of code that were independently deployable, versionable, scalable, had unique names, and were addressable. And let's talk you through the reasons why. First and foremost, when you build and run a service, scale is unpredictable. You might start off with 3 machines, you might go to 30 machines, you might go to 300 machines. You don't want to be able to re-architect your app constantly because of the scale demands, whether they scale up or scale down. Secondly, there's this concept of agility. We spent years sort of as an engineering team building a big box product. We shipped that every few years, and all the engineers were focused on that. And as you run a service, we had to become much more agile. In fact, it had a fundamental change inside the engineering teams at Microsoft. The SQL Azure teams, for example, changed from focusing on box product features for a DevOps style where they run a service now. And that meant they had to have agility. Individual teams had to ship and deploy individual pieces at different times. So, for example, when you're SQL Azure, there's a team that builds the database microservice, there's a team that builds the protocol gateway service, there's a team that builds the backup and restore microservice. And each one of them had to build a ship in their own schedule at their own time frame. They couldn't wait for each other. So there's a lot more agility in getting their things rolled out, new functionality, fixing bugs, and each one of those had to be coordinated across a set of machines, and you had to be able to do the versioning, the deployment, and the upgrade of all those. Next, of course, came resilience. It was important to be able to have, when you're running a scale set of machines, when you're running hundreds of machines, when a single machine fails, you can't just simply go, what was on that machine? How do I recover the state on that machine? How do I redeploy the services running inside that machine? You have to be able to deal with automatic failover. You have to be able to do self-healing of the service itself. So you want to be able to say, look, a machine failed. I just want you, Service Fabric, the underlying platform, to take care of making sure that those services get redistributed against the remaining set of machines that run there. Then, of course, came cost. If you look at cloud services today, if you want to spin up 5 worker roles, you have to spin up typically 10 VMs and place them across there. And we've often been asked, why can't I just run all these different worker roles on the same smaller number of VMs? Well, this is exactly what Service Fabric does. We break things down into microservices, and we can deploy hundreds of microservices onto a small set of VMs. We can start off with 3, we can go to 30, and go to 300. So we can packly dense those, and it helped us reduce costs. When you start to run these services at scale, cost becomes a very important factor. So all of this drove us to build a platform. We use this internally with all our services. The bits that we gave out yesterday are exactly the same bits that we run inside our data centers. In fact, we just cut the 4.0 release, what we shipped a few days ago. The actual 4.0 release is still being rolled out inside our first-party services internally, so you've even got it before some of our teams have deployed. And we're sort of thrilled to be able to say that when you take this and deploy it on your machines, you have the same code that we use inside our services. And even more so, our objective is that we're taking this platform, and not only will you be able to take those applications that you build against this SDK and run them in a service that we run inside Azure, but also we're putting the same platform directly inside Windows Server 2016. And what that means is that you'll be able to build those applications. You can run them inside Azure with no code changes. You can set up a cluster of machines on Windows Server, and you can host them inside your private clouds. You can host them anywhere where Windows Server 2016 is running. And of course, beyond that, we're also looking at how we port the whole platform over to Linux and host that on a OS of your choice. So now you'll be able to say to choose the OS of your choice, and you'll be able to choose a location of your choice. And of course, the whole platform is designed that you can either build against the APIs that we provide, or you can bring your own runtimes about how you deploy that as well. So it's incredibly flexible, and we're very excited to be able to say this is the way that we think about how you should build scalable, resilient applications. So let me get just a few concepts in place, because understanding a few of these concepts helps you really appreciate and understand the demos that we're going to run through. At its core, we talk about a cluster. And what this does is we take a set of machines, physical machines or VMs, and we stitch them together to form a cluster of machines. And this cluster can be scalable from 3 machines to 30 machines to 300 machines. It's kind of infinitely scalable. You can scale it up, you can scale it down. It consists of machines of different sizes. But it's important because you can think of this as a collection as a whole. What happens then is that you come along and you define and build an application that consists of microservices, pieces of code that you can decompose into your application. So you think very much about design in terms of componentization of your application. What happens then, this application, which is sort of a logical collection of these services, you can build many of them, and you simply say to Service Fabric, deploy this application into the cluster, and containing microservices distribute across the set of cluster of machines in the most efficient way. We understand the resources of the actual microservice that it uses. We understand the resources of the machines. We do the most efficient placement around all of that. Of course, what can happen typically is you deploy these microservices across a set of machines, and of course, we're all about resilience and failure. And it's, it's a thing to have in a distributed system. There are machines that will die. That's the inevitability of having commoditization of hardware. We want to be able to have cheap commoditization of hardware where you want to know that if failures are not going to bring down your service. Well, if that's the case, we simply go, we understand exactly what was running there. We knew exactly the microservices that were there, and we simply look how we redistribute them around the remaining set of machines inside the cluster, and as far as you're concerned, all of this transparent failover makes sure that you have constant high availability and resilience in your service. This is how we build large-scale, mission-critical services that we run on, like SQL Azure databases, DocumentDB, event hubs, Intune. This is a critical part of how we make sure that there's a full resilience inside a cluster of machines. And of course, this cluster as well can span multiple data centers or multiple regions, so you can provide resilience beyond the bounds of just a single region itself. And in fact, if you take one of the services that we run, which is the back end of Cortana, they spread that across 3 different Bing data centers where they run this. So given that little bit of a background about the concepts, let's talk about what you can actually build. What we do is we split applications into typically 2 types. We talk about stateless services, and we talk about stateful services. Stateless ones are something that you're probably almost exactly familiar with today. They're the concept of things like cloud services today, worker roles, ASP.NET applications. All the state gets externalized to some store, like whether that's Azure storage or SQL databases. And typically, when that piece of code starts up, it pulls the data from the store and does its computation on it. And if that particular service goes down and gets instantiated somewhere else, it reloads up all its data. But one of the great innovations, in fact, an enormous innovation that we were forced to build was this concept of stateful services. And stateful services have 2 huge benefits. One is that they reduce latency. And what that means is when requests come in from your client, the state and your code are co-located together. We take the state of your application, the data, we make it highly resilient by persisting it locally and making replica copies of it. So now your compute and state are co-located together. And that reduces the latency enormously. So you don't have to go to some back-end store and to pull all your data back. Secondly, and critically, is that stateful services actually reduce the complexity of your application. When you start to think about stateful services and you start to think about designs today, I'm almost certain that you've built applications and services today where a request comes in from a client, it goes into a queue, you pull it out from the queue and you put it into your worker role, and then from that worker role, you then push into some back-end store. And then typically you probably have some caches where you can improve the read latency from that back-end store. Well, one of the key aspects of stateful services is what we've effectively done is we've democratized HA. Okay, we've given high availability to all of you as part of a programming model that's simple to consume. And what that means now is you can get rid of those externalized queues and get rid of those externalized caches because your application is naturally highly resilient. You don't need to have a queue inside here. Your application is naturally cached to the data. It's simply the data is made resilient and replicated across a set of machines already in the middle tier where you run your code. And so it deeply simplifies how we do these things. Let me give you an example. The back end of Cortana, where you run, runs across a cluster of 120 machines. They built a stateful service that gets run. They have about 1,000 instances or more of the microservice they run. And one of their stateful services they build is a query engine. And what that query engine does is it has a number of subscriptions. It runs link queries across incoming data feeds. So lots and lots of data is coming from traffic, it's coming from finance, it's coming from weather. They have huge numbers of these microservices run. They have a query expression. They evaluate millions of these query expressions across a partitioned set of services. And anytime there's a failure in one of those machines, all those query expressions are replicated across another service that's running. And so you get very fast failover. And that's an example of the statefulness that they have. Fast failover where they can actually do query expressions against the incoming data. And when they hit one of those query expressions, for example, your GPS location and tell me where there's a traffic alert, they send off an Azure notification. If they were to build that as a stateless service, pulling all that data in and running all those rules, and when there's an event of the failure, the failover and loading up all those subscriptions would give you a very slow experience for you to be able to have a fast responsive time in terms of making sure you have notifications about what happens. And finally, we provide this runtime that allows you to build stateless and stateful services, but of course we can completely embrace any other runtime that you want to deploy in terms of what we call a microservice, whether you use some Node.js or whether you use an arbitrary XE, we'll deploy that, we'll make it fully resilient. If you want 10 copies of it running and one of the machines failed, we'll make sure that that always gets running somewhere. So you can bring your own runtimes, combine that with our runtime. And typically what we find is that many applications consist of some stateful, some stateless services, and different runtimes, and all of this gets composed together and managed as a single entity across Service Fabric. So how is it you're going to build some of these things? So effectively, we have two programming model APIs. We have one that we call reliable actors, and then one that we call reliable services. And both of them take advantage of the full platform capabilities. And using either programming model API, you can build microservices and be able to compose your applications from those. And typically, we find that many applications we have compose from both programming models in terms of how they design this. Whichever you choose, you have the advantage of the full platform underneath it all. So what I'm going to do is I'm going to hand over to Vipul, and he's going to talk us through what are some of the advantages of what he means by actor.
Yeah. So, hi, everyone. So the Reliable Actor API basically allows you to harness the full power of Service Fabric by using very simple programming model. It's a virtual actor-based programming model. It's suitable for like IoT or games where you can actually divide your state as well as logic into very small independent units, and they can all run in parallel. The runtime provides you basically automatic state management, and as well as it provides a very simple turn-based concurrency. What it means that you don't have to write complicated synchronization logic. You do not have to write complicated code to save your state to some backend database and make it reliable. The platform takes care of that for you. So now let's go ahead and look at building a reliable actor. We'll start with a stateless reliable actor, and then we will go and make the state more reliable. So I'm going to switch over to Visual Studio. So you'll notice in the SDK, we have done a full integration with Visual Studio. So when you create a new project, you'll see the templates, which are basically you can create services using Actor, or you can create services using the Reliable Services programming model. So here, I have already created a project using this template, which is the stateless actor service. In this case, my actor is so there are three things that you need to do in order to build a reliable actor. First, you define the interface. So actors are just like objects. So you define an interface. In this case, I'm defining a counter actor interface. It obviously has a set method in order to set the count, and a get method to get the count. And a more appropriate set method, which is a compare and exchange method, right? So that's the first thing that you do. The second thing is that we have to go and implement this counter. So you go ahead and implement the counter. So in this case, I'm implementing the counter. The value is stored in a member variable. So you derive from an actor, and then you implement your actor interface. And the compare exchange is doing a normal compare exchange. Look at this code. In this code, we have not written any synchronization logic. We have not written any state management logic, activation logic, nothing of that sort, right? It's a very simple code. It's like any other class that you would write. The third thing that you need to do is to basically register that actor with the runtime so that runtime can activate it as needed. So here I create a fabric runtime. I register the actor, which is my actor, and I wait for the activations to happen. So let's go ahead and deploy this actor solution into actor application into the local cluster that we have. You'll see that, so while it is deploying, let's go ahead and look at how would you actually use the actor. So in order to use the actor, you connect to it through what we call an actor proxy. So actor proxy provides location transparency. It allows you to identify the actor using the actor ID. And you can identify the actor either through a string identifier, or you can use a long, or you can use a GUID. So you say, I want to connect to a counter actor, in this case, counter 1, and you create a proxy to it. So now the actor proxy will provide you location transparency. It will connect to the right actor. It will dispatch your method. If, let's say, that actor were to fail and the runtime were to reinstantiate it somewhere else, it will transparently reconnect and your calls will go through. You would not have to handle any failover logic whatsoever. So in this case, what I'm doing is that I just get the counter value, current counter value, and then I increment the counter value by adding 1 to it, right? Now let's see what is deployed in the cluster. So this is my local cluster. It's running on this laptop. It's running 5 nodes on this laptop. And it's running exactly the same code as it would run in the data center. There is no difference. This is one of the big difference with respect to the previous cloud services iteration and this, whereas in the previous cloud services, there was an emulator. Here, there is no emulator. It is exactly the same code. So if your code runs on your machine, you know that, yes, it will actually run in the production environment as well, right? So I have 5-node cluster. Let's see. So the application is deployed. This is a counter application. And it contains 1 counter service. So here is the application. This is the service. It has 1 partition, right? And that partition is running on node 4, right? So let's go ahead and look at on node 4 what is running. So on node 4, you can see that we have our counter exe running on node 4. And it has 1 instance placed in that node. So now I'm going to go back and run the client. So the client is connected to the actor through the actor proxy. As we saw in the client code, it's basically incrementing the counter, right? So now I'm going to put this to refresh. So you'll see what happens. The counter is actually on node 4. So I'm going to go ahead and restart this code on node 4. So you saw that the system took failover action. The actor proxy transparently reconnected the client to another instantiation of that actor. And, well, we lost our count. So we lost the state, which was expected because we were storing the state in a member variable, right? So we made the code reliable, but we didn't make the state reliable. So let's go ahead and look at how can we make the state more reliable, right? So I'm going to stop the client.
So that's exactly an example of what we're talking about from a stateless service. Okay, I've had failure, I had to recover, and I recovered my state from either from the beginning because I started the computation or because I pulled it from some externalized store.
Right. So I'll go back to our counter actor implementation. So in order to make this a stateful reliable actor, you need to define the state. You can define any state that is serializable. So in this case, I've defined a counter state which contains a value for the counter. Now, rather than deriving from the actor of actor, you will derive from actor of T state. So in this case, it's counter state. Right? Now that we have derived it from a stateful actor, we do not need to store the member variable. So we'll comment this out. Now I need to get this value from a base state property. This property is the reliable state. So when an actor is instantiated, we hydrate this property with the last consistent value. If you make changes to this property, when your method returns, it automatically gets saved. So this is the automatic state management that I was talking about. So let me go ahead and modify all of this code. Shouldn't take long.
And so what you'll see in the beauty of all of this is now the state's contained as a stateful service. And when we'll do the failover again, you'll see a completely different experience.
Right. So again, as you saw that I did not write any synchronization logic here. The turn-based concurrency is provided by the runtime is taking care of the synchronization for me. So whenever any of these methods are in progress, it is guaranteed that no other method is being called. So you can make changes to your state just like as you would in a normal .NET class without worrying about concurrency. And so in the set method, when we set the value of the state, once the method returns, the state will be replicated to n replicas and quorum committed. So let's go ahead, deploy this solution again.
Notice the fast deployment times here. You see it's seconds to deploy your service now, as opposed to cloud services today. It's just a few seconds and up and running, and your service is deployed. One of the great benefits as well we have with this platform.
Actually, I wanted to do one more thing, so I'm going to redeploy it again.
Great. Redeploy all the time. I mean,
so I wanted to put a breakpoint here and show that we have already integrated the debugging capabilities in the platform as well. So while I deploy, the bits actually go on to those local cluster. The process gets activated, and then the Visual Studio connects to that and attaches that and gives you the complete debugging experience. So I'll go back and go to the client.
It'll hit that breakpoint. See that fast deployment time?
And our breakpoint is hit. So the client is saying that I want to set a value of 1, and the previous value was 0, which was true because we just activated this actor. So I'm going to press F5 again. We know that the client actually does this in a loop, so it will come back and it will say, hey, why don't you set the value to 2? The previous value was 1. So I'm going to remove the breakpoint, let this go, detach the debugger. And as you can see, the client is going, it's incrementing the value. So let's go back to the Service Fabric Explorer and see what got deployed. So I'm going to refresh this. So this time, you'll notice that I have one partition, but I actually have 3 replicas. I have a primary and then 2 secondaries. So as the state changes are done on a primary, they get replicated onto those secondaries, right? So,
and that's exactly how we make a resilient stateful service. Yes, we have copies of your state replicated around. When you kill machines, we know exactly where they are. You never lose any of your data. We build SQL Azure databases is built exactly like this, yes? Copies of databases, machine fails, we just fail over to the other copy.
Okay, so you know what I'm going to do next. So I'm going to actually restart this primary. Notice what happens in this area as the failover happens, as well as to the client. So you can see a replica went down. Immediately another replica was selected as a primary. And then you can see here that we did not lose our state. We started from the same state, right? You can
That
clap.
surely is a round of applause.
So that's how easy it is to build reliable stateful services using actor programming model. Let's switch back to, so there are a lot of features in the actor programming model that we haven't shown. We have a recorded session that you can go and watch so that we can move over to actually talking about the reliable services programming model. So please go to this session and then watch it whenever you can. We talk about in depth all the features that the reliable actor API provides. So back to you, Mark.
OK, so let's talk a little bit about what you saw, and we'll build on another concept here about how we package, deploy, and instantiate these applications. It helps you understand how the microservices concept is very important and how you think about architecting your applications. So its core concept, you think about writing some code that typically also has some configuration associated with it. And you take that code and configuration, and you package it together, and you put that into what we call a service package. That package has a manifest representation of it, and this represents a unit of deployment. Okay, and think of this as simply as a CLR type. Well, what you do next is you say, I'm going to define an application package. And my application package is like a container for the service packages. It defines a boundary of versioning, defines boundaries of isolation, defines boundaries of lifetime of it. And in itself, then you can take and you can put the service packages inside here. I can define a service package for a service I've had here called the counter service type. And I can come along and define another service package here, and this might be a web application, and this will be called the counter web application type. So I've got two types of services deployed inside my application package, which provides a logical boundary around them all and gives the units of lifetime versioning and isolation. And that thing itself is defined as a type. So what do I do next? What I do now is I've defined these types. I upload them into Service Fabric. We have inside there a service that's called the image store, where we define all these, hold on to all these package types. And what you can do now is you come along and you take these package types, and you're going to create instances of them. So remember, what's straightforward. A service type is like a CLR type, and an application package is a container for multiple of those service types. And now, just as you think in terms of an object orientation mechanism, we create instances of these things. So I can create an instance of an application type, and inside that instance of that application type, we create instances of the service types that it contains. So I go to my cluster, and here at this point in time, I say I'm going to create an instance, and every application instance has a name associated with it. So in this case, it may have a name, say, fabric/counter application. And then when I say to Service Fabric, I want you to deploy the contained service type and create instances of those, and each one of those instances of those microservices have a unique name associated with them. For example, here I've deployed one of the counter service types, and the other one is the counter web application type. We create instances of those that are associated with that particular application package instance. So as a result, you can have, in the same way you think about types inside CLR, I can create hundreds of instances of a particular application type. They all have a particular versioning. I can upgrade and downgrade any particular one of those, and you have the set of instances that are associated with that type. So this is how we think about defining a microservice, packaging it, and deploying it, and then creating instances of it all. So we're now going to look at the next programming model API, and we're going to get Vipul to go and dive into the benefits of how we think about reliable services.
So we looked at the actor APIs. It was pretty simple to build stateful and stateless services. Now, if you need more control and more flexibility, you want to use reliable services API, you also can build a very powerful stateless and stateful application. So for example, let's say if you are using an existing ASP.NET app, you can host it as a stateless application inside Service Fabric using reliable services API. You can also build powerful stateful applications using reliable collection, which we will talk in a bit. So in the actor APIs, we talked about how there was a turn-based concurrency, and then any changes that you make into your state get saved at the end of the method. Well, for the reliable collection API, reliable services API, using the reliable collection API will give you more control in terms of managing the concurrency as well as the granularity of your update. So you can actually have multiple simultaneous updates happening to independent keys at the same time, and you can achieve a high throughput applications. You can also communicate using the technology of your choice. So for example, for the actor APIs, we were using actor proxy. And we did not know what transport it was using. It just independently provided a connection between connection to our actor. For the reliable services API, you can use WCF, you can use Web API, or you can use what we call a service proxy, just like actor proxy. Or any other protocols you may have. You can use raw socket, TCP, FTP, whatever you prefer. So it provides more flexibility in terms of communication, right? Now, building stateful services is really, really hard, and getting it correct is really hard. So what we are doing is that we are providing you the same familiar concepts that you have known for years in order to build your applications using .NET. So previously, we used to build applications on a single machine, single-threaded, using .NET collection. We then started using concurrent collections in order to provide multi-threaded access. So think of reliable collection as a natural evolution to that. It's a collection that basically spans multi-machine. It offers HA. It's durable, and it's transactional, right? So what are the two? There are two reliable collections that we offer out of the box. So you can use a reliable dictionary of key and value, or you can use reliable queues. You can atomically update one or more of these collections. So you can instantiate one reliable dictionary inside your service, or 10 reliable dictionaries. You can instantiate one queue, 5 queue, or 5 queues and five dictionaries. It's up to you. And you can atomically update these collections using transactions. So the transactions span those reliable collections. The changes that you make are replicated, and they are durably stored on multiple replicas within the cluster. The reads, when you are within the transaction, the reads are repeatable. And the enumerations, when you enumerate this collection, they give you a consistent snapshot of what is there in the collection. So now let's go ahead and build a reliable service. So this time we're going to build a word count service. I'll switch over to Visual Studio. So I want to build a simple word count service, which you can add words to it. As the words are added, it's counting the occurrences of those words, and it is also counting the total number of words that it has seen so far. And this getCountAsync method basically returns what is the total count of the words that have been processed. You'll notice here I'm using WCF. This is the WCF contract in order to connect to the service and then add the words or get the counts. We'll see other form of communication as we go along in the talk. So here is the stateless service. I derived the stateless service from my word count stateless service from a stateless service. I implement the word count service interface. Here, this is a stateless service, so I naturally want multiple threaded access, so I'm going to use concurrent collections, right? So I'm using a concurrent queue in order to, as an input queue, so as the words arrive, I'll put the words into the queue. So if you look at the add word implementation, you'll see that as the words arrive, they're just enqueued into the queue, right? Then I have a dictionary that basically keeps the count of those words. And then I have another dictionary that basically contains the total number of words processed through a key, which is total word process key. I could have used actually just a member variable here. I'm using this to show how you would map that when we build the stateful services. So there are two things that happen when a service is instantiated by Service Fabric. First, we go ahead and ask the service, hey, give me your communication listener. And that communication listener has very simple open, close, and abort method, and the open returns a string. This is the address on which your service is listening. So when your client asks you, hey, I want to resolve this service, you saw that the services had names. And so when the client asks, hey, I want to resolve this service, this is the address that we provide to that client. So in this case, I'm using WCF communication listener. This is one of the type that we provide as part of the reliable services API. So there is nothing here that's extra. You just do new WCF communication listener, give your contract, and say this is the class that implements it. The second thing that happens is that once the service is ready, a run async method is called. Think of this as the current run method in your worker role, right? So this is where you're doing most of your processing. So in this run method, you'll notice the cancellation token here. So this cancellation token is valid as long as this instance of the code is the one that is, in the stateful case, is primary, or in the stateless case, is the actual instance that is handling the request. Let's say due to a load balancing movement, this instance gets moved to a different node within the cluster. This cancellation token will be canceled by the runtime, and then you can react accordingly to say, hey, if the cancellation token is canceled, I'm going to stop doing the processing because another instance will get started on a different node, and the run async method of that instance will get called. Okay? So I'm doing a simple dequeue here. So I say as long as the items are available in the queue, I'll dequeue, and then I'll count the word in the dictionary, and then I'll update the total number of words processed. Right? So let's go ahead and deploy this service in the same cluster. So while the deployment is happening, let's look at how do we use this service, or how do we connect to it. In case of actor, we connected using actor proxy. In this case, I've written a client. That client says, here is the URI of the service. And when a word is being added, it says, I need to look up where this word is, or what partition is serving this, this word. We'll talk about partitioning in a moment. Right now, the service is single partition, as we were seeing even in the actor case, as well as in this case. The service is single partition. And we create what we call the service partition client. This represents a logical connection to my service, correct? And in this case, you know that we are using WCF. So your word count service partition client is deriving from a service partition client of WCF. And it's implementing add and get count. When an add method is being called, it asks the base class, hey, give me the actual physical channel. So the base class gives him the physical channel, and then it goes ahead and calls add word async.
Now
This
we're also going to provide, I mean, we also talk about this WCF communication listener, but there's also going to be our ability to talk through web API, yes?
correct. So we'll show, we'll see that in a moment as well, right? So here the service partition resolver, which is provided as null, so we use default service partition resolver. This associated with this WCF client communication factory is providing you the location transparency and the caching of the channel. And again, this comes as part of the reliable services API. So I think the service should have been deployed by now. Let's go ahead and look at that. So we have our word count application deployed. We have both stateless and stateful. We'll look at the stateful in a bit. So this is the stateless word count service. It has obviously a single partition and one instance that is running on node 1. Okay? So let's go ahead and fire up the client to it. So this is a beautiful console UI client. You can see that it's just adding the words and it's getting the counts continuously. So now let's go back, and I'm going to go ahead and restart the replica restart the code package on node 2. So here is a word count application, stateless service package. This is the code, right? I'll restart the code. You'll see that the count stopped, right? Well, it did start, but obviously we lost the state because we were storing the state into the concurrent dictionary, not actually the reliable collections, right? So this is what happens when you, so you made the code reliable, and then we'll talk in a bit, how do you make the state reliable, right? So I'll jump back to the PowerPoint presentation. So what do I need to do if I had this application today in the current cloud services? How would I make it actually reliable, right? So the first thing that I have to do is to that input queue that we had, which was the concurrent queue, I have to make it reliable, so I'm going to use Azure queues, right? And then in order to, I have to store the dictionary into the counts that I'm doing for the words into the Azure table or some other NoSQL table, right? So this is what it would look like. So whatever is this on this side, this is what would look like if in the current architecture, not with Service Fabric. So with Service Fabric, you'll basically get a request from your front end, and your back end is a stateful microservice. It's using this reliable collection, which are dictionaries and queue, and they have multiple replicas, and they're basically making the state reliable, right? So you reduce from a typical 3-tier architecture with a front end, middle tier, and a back end to just front end and your middle tier, which is your business logic. So your state and compute, as Mark mentioned, is co-located together, right? So let's go back to Visual Studio.
So I mean, the point is you can build stateless microservices and deploy those, but you can also build stateful ones as well and take advantage of those. So you may have some existing code that you just simply want to be able to say, I want to be able to deploy that in a microservices way and take advantage of that. But you can also take advantage of how we improve on that design concept by using statefulness, and that way reduce the complexity on particular pieces of code that you run inside there. And as you say, typically in most applications we see both. We see stateless gateway front ends, and then we see for a lot of the business logic, say shopping carts, say database-like microservices built in terms of a stateful microservice with our stateful APIs.
Right. So this is the same word count service. Now it's a stateful service. You'll notice here is that I'm deriving from a stateful service rather than a stateless service. I'm still implementing the same word count service interface. I have stem, create communication listener, and run async method. Let's see what happens in add. So previously, when the add was called, we were basically putting the item into the concurrent queue that we had as a member variable inside here. You'll notice there are no member variables here. So what we do is that we go ahead and ask the state manager that's in the base class, which is a reliable state manager, to say, hey, I need an input queue. I need a reliable queue. Here is the name of the queue, which is the input queue. And the name can be a string, or it can be a URI. And you can have multiple ones of those. You just ask the state manager, hey, I want to get a reliable collection. So in this case, I'm getting a reliable queue. Once I get the reliable queue, I can enqueue an item into it and commit the transaction. So once the transaction is committed, this item is reliably present in the cluster. It's replicated to n set of replicas within the cluster. And then, again, for the communication listener, I'm using WCF. For the run async method, I have an input queue. I have a word count dictionary and a stats dictionary, same as previously. But instead of a member variable and a concurrent dictionary, I am asking the state manager to give me reliable dictionary and a reliable queue, right? So this is the difference. This is how you would get hold of your reliable collections that you want to use within your service. Again, until the cancellation is requested, I'm basically getting the items from the input queue. And if there is an input queue item, I'm adding the item into the dictionary, counting it. If there was already an existing item, I'm increasing the count. And then I'm saying that the total number of words processed, update that as well, commit the transaction. Now, this is important. All of these three updates that I'm doing, I'm dequeuing an item, I'm modifying another collection, another dictionary, then modifying another dictionary. All of these are atomic, which means that if my process were to fail somewhere here, the item that was dequeued using this method is actually not dequeued until the transaction is committed. So this is the guarantee that we provide, that you can modify multiple collections atomically and update them atomically.
That's a super important thing. Think about it. If you write code today and it fails, how you have to do all of the recovery and the failures inside that. And here we're providing transactional guarantees around updates on those dictionaries to make sure that until that commit happens, we'll provide full consistency on the transaction, we'll roll it all back to where it was.
Okay, so I'm going to then fire up the client, connect to the stateful service. You'll see the words are being added and they are being counted. Let's go ahead and go to our application. So here is a stateful word count service, right? It has one partition, and just like for the stateful actor, it has 3 replicas: a primary, and a secondary. Primary is on node 3. I'll put this into refresh. We'll go ahead and restart the primary on node 3. Let me move this down. So primary replica has been restarted. Another replica became the primary, and you can see that the counts are going on, and then we haven't lost any count. Previously, we lost the count, so the state is reliable. The service is still functional while a primary went down because there was a very fast failover. Another replica became a secondary, became a primary, and then I was able to continue the operation. I was able to continue the operation because this is a quorum-based system. So out of 3 replica, 2 replicas were available. So I'll do this again just so that you can follow along.
So this is what we talk about, we've democratized HA. You just build apps, use simple program model APIs. We'll guarantee the HA and the availability of this. You can attack processes, you can take down machines. We will always make sure there's a copy of it inside the system. We challenge you to actually fully attack this system. This is exactly what we do all the time. In fact, the full reliability and consistency of this is how we rely on providing full transactional stateful services that we run all our heavy workloads on today, like SQL Azure and DocDB.
Okay, so I'm going to restart the replica. The replica is now on primary, is on node 4. You'll notice a switchover happening right here. So this became primary. There was an active secondary. The counts are going while this replica is still down and it's building. So after a while, what will happen is that we'll start to build up this replica. This replica will come up. It will show as in-build, which means that while this replica is down, there is a bunch of operations happening. All of these operations, the words that are being added, that replica needs to be caught up to those. So it becomes in-build. We're basically saying that, OK, you still cannot join the replica set because you don't have all the operation. Once it has all the operation, it will become an active part of the replica set again. Right? This is so now we have seen how we can build reliable stateful services using actor programming model as well as the reliable services programming model. So now Mark will talk about, well, we have this word count app. It had a single partition. Obviously, we know that's not scalable. So how do we go ahead and scale this service?
Yeah, so a key concept of this platform is the fact that partitioning is first class. You could have a scale-out partitioning design in order to build high-scale distributed applications that can run across hundreds of machines. A lot of the time, you have to, partitioning is left up to you as a developer. Inside this platform, we say, no, partitioning is a first-class concept. And how you do your partitioning, we provide different mechanisms for you. We provide range-based, in64-based partitioning or name-based partitioning. Effectively, you come up with the partitioning scheme you want. Say you want to use zip code as a partitioning mechanism. Say you want to use an ID mechanism. You can easily build that into your choice in terms of the client request that comes in. You look at some piece of information, and then we'll simply say, how do you want to send that particular request to a particular partition? So partitioning is just exactly you would think in the typical concept of scaling out any application. Here, I segregate my service into pieces of state and code, and I send a particular request to that location where that state and code is co-located, and how I separate that out across hundreds of thousands of partitions. So we think about this as when you build your service, you say, think about your partition requirements. I might need, say, 2,000 partitions. And you can deploy those 2,000 partitions across any number of set of machines. You might start off with, say, 10 machines. And then you can grow the number of machines inside a cluster. So what does it look like? Typically, when you deploy inside your machines, a partition gets deployed on one of the nodes inside the cluster. Of course, it creates replica copies across other machines in there to make it highly available. You then think how it deploys a second partition for that service on another machine and makes copies of that, and then a third on another machine, and a fourth, and so on. And it keeps pushing the top partitions across all these. Now, you can squeeze all those partitions down onto a certain number of machines, and as your load on any particular partition grows, you can say, simply add new machines, we'll move the partitions out, and scale accordingly, and all of this is entirely transparent to you. So, for example, say one of those partitions came particularly hot and had a lot of data, we'll say this partition's got more than the rest, we'll find a machine that's got the best utilization of the resources, and we'll move it onto that machine. So as a result, this partitioning concept enables you to truly think about high-scale distributed systems where you simply have to just understand what's your partitioning scheme and your partitioning concept. And we take care of striping and pushing those partitions across the machines inside the cluster and dealing with all the failures inside that, of course, and dealing with whether some partition is hot compared to the others and moving them all around. So let's now think and look at how we're going to take that same application, that Word application. What we're going to do instead, we're going to have a client front end where requests are going to come in. Think of that as a bit like our load balanced front end where we have a web API. We're going to look at the request that comes in, and now we're going to look at the content of that, and we're simply going to scale out that request from that particular client to a particular partition. So we take this word count service, create numerous partitions for it all, and now when the request comes from the client, hit the web front end will kind of look at the request itself and send it to a particular partition. And you can have any number of partitions easily scaled out, in a declarative mechanism inside here.
Okay, so let's switch back again to Visual Studio. So this is an application manifest. This is what Mark was talking about. So when you define an application type, you define that in the manifest. So in this case, as you can see now, I have a word count web service, and I have a stateful word count service. My stateful word count service is partitioned. It has 13 partition, and I have both web service as well as the stateful word count service in the same application. So there are two service packages. So you saw the slide where there were service packages, and they were animated and put into that application package. Well, this is the application package, and here are the two service packages that are defined, right? A web application package, web service package, and a stateful service package. So now let's look at what does the service looks like, right? So in this case, for the stateful service, everything remains exactly same, except that I have basically used, instead of WCF, a service communication listener. So this is, we provide a communication listener out of the box that you can use. Remember on the previous case where we were using WCF, I had to implement some code. I had to implement that word count service client, derive it from a service partition client, and do a bunch of work. No longer I have to do that. Basically, if I use service communication listener, just like actor proxy create of iActor interface, I can do service proxy create iService interface, and I'm done. I will get a transparent channel to my service, which actually provides location transparency. And so the contract looks exactly same, except that there are no WCF data contract operation contract. Instead, it's deriving from iService. So that's one change I have made. The second change, as I said, I have made is to basically add the web service and then change the partition count. In the web service, I'm using Open Communication Listener. So this is actually a front-end service. The clients will connect to it through typically a REST API. And so the Open Communication Listener provides that. So I'm hosting an ASP.NET application and creating a stateless service. So this is word count. Web service is a stateless service. There is a stateful partition service, correct? So now let's see how it looks like inside the cluster. So inside the cluster, as you can see, I have multiple partitions. I'm going to show a different view of this using what we called a cluster monitor. This is, again, a sample application that we have written. So both the Service Fabric Explorer as well as this are using our management API. And these APIs are public. We also provide REST-based APIs that you can use in order to manage or query your state, query the cluster. So I imagine that some of you will actually say, hey, the Service Fabric Explorer is good, but the UI is not that great. Maybe we'll build something more appealing and more pleasing to eyes. And you can do that using the APIs, the management API that we provide, right? So here, the same slide that Mark showed, you can see that there are multiple partitions. So each of these black boxes represents the node. And inside that, multiple applications are deployed. And within that, I have multiple partitions. So when I hover over a primary here, you'll see the two secondaries corresponding to that are being lighted, right? So now let's go ahead, and this time I'm not going to do failover. All I'm going to show you is that if a node were to go down, so this is node 3, if a node were to go down, so let's go ahead and shut down node 3. You'll notice that we take failover action, and all of these primaries that are located here, they will switch, and they'll switch to a different node, as well as all of the active secondaries that are marked as down. So now that partitions that were here, the primaries that were here are still available. This is the same failover in a different visualization, right? So I'll go ahead and re-enable the node.
So this is the self-healing aspect that we have. Think about this. This is exactly how SQL Azure runs. They have hundreds of thousands of databases. A machine dies. There was 100 databases on that particular machine. We know exactly what was running there. We fail them all over to another machine. As far as the client is concerned, it's completely transparent. We do an automatic failover to a secondary copy, allocate that, and elect that to become a primary. The client connects to that, and there's no loss of service. The machine may come back up again. We'll say that's available as part of the cluster again, and then start to place new primaries and new secondaries on top of this. So as far as you're concerned, machines go, machines arrive, and this transparent moving of these microservices around them all is completely transparent to you and deals with this sort of self-healing system. Let's take the questions at the end. We are nearly there.
So because I didn't start the word count web client, I started the word count web client and shut down the node again. So you can see that the word count web client is going on while the node went down. The primary failover happened, and then transparently we relocated the primary, and then the word counts are continuing to happen. These are the count across various partitions that are there, and this is the total count across all of those partitions. So I'll go ahead and start the node again. And then what I'm going to do is that I'm going to enable, so in order to test your application, so first of all, writing stateful services is hard. We have made it very simple using reliable collection, but there is still going to be certain things in your business logic that you have to take care when a failover happens. And you may say, hey, well, the failover happened, but I am not sure whether I'm doing the right thing. So I want to test my service. So we included this chaos service. This is part of the system. So the chaos service starts taking action. It basically restarts the code packages. It restarts replica. You can see certain things happening here. It'll restart nodes. It'll ensure that cluster is healthy before moving on to the next round of the faults. And so you can continuously run this in your cluster and make sure nothing bad happens. Your clients are happy. Your clients are continuing. And you know that your application can survive different kind of failures, right? So before we go over to summary, I would like to take this opportunity to thank each and every member of the Service Fabric team who have been working hard at this technology for a lot of years, as well as all of our internal partners and customers.
Yes.
Let's
switch over to the last couple of slides here. So to summarize, we're pretty excited that because of the way we thought about how we had to build our high-scale services, we realized that when we moved from these box products to these services, we were naturally thought about how we decompose these box products into a concept of microservices. And it's very important. There's a lot of talk around containers and what they are, but you don't design with containers. You design applications, and applications get broken down into pieces of code, and those pieces of code are what constitute your application. And that's how we think about a microservice-designed application, what it means. The fact that those microservices get deployed inside containers for isolation and security is part of the characteristics that you say of the requirements that you want of the microservice itself, how it gets deployed. So, and we've been building this platform a number of years. We're very confident in it because we know that we run it ourselves. We're thrilled the fact that we've given it to you. In fact, the bits that we shipped this week, as I said, are still being rolled out across a lot of our first-party clusters. And hopefully we've shown to you that we're using very simple programming model APIs of the actor side of things and the reliable side of things. You can go away and build stateless services like you're very useful. You can take advantage of stateful ones as well. You can compose your applications of multiple pieces of code. You deploy them together as an application. You can take existing code, like you might have Node.js application or arbitrary executables, wrap them inside those service packages that we talked about and put them inside an application package and just say, hey, I just want you to make my Node.js applications reliable. I just want you to deploy them. I always want 10 instances running. If I kill machines, just make sure there's always 10 instances running. That's all what we refer to as part of our microservices architecture and how we put these things together. But of course, if you take advantage of our runtime that we showed you today, we have deep insight into your application. We can provide as a health model that we haven't dived into. In fact, I fully encourage you to, after this, there's going to be a session that talks all about the deployment, the life cycle, the management of all of this. Because although we've shown you how to develop apps here, the biggest cost by far when we run one of these services is the day-to-day management of these things. Think about SQL Azure. They have hundreds of updates a day across thousands of machines, different versions that run. We have to understand the health, the monitoring, deep insights to what happens here, all of this transparently. So after this, we'll have a session in the room next door that tells you all through walks you through the life cycle and what this looks about, how do you manage these services. So hopefully you've given appreciation of all of this. Our call to action is please go and find the developer SDK, download this SDK, go and get the samples off GitHub, the word count sample and the other samples you saw here today are available there. Go and read some of our docs to get yourself started. We have lots of feedback forums. We want you to go to our feedback forum at aka Service Fabric Forum. Give us lots of feedback. We're on the user voice. This is the beginning of the journey for us, where we're going to ship the regular SDK. Later in this year, we're going to provide a service inside Azure where all your applications that you've built, you'll be able to run inside Azure. Later on, further in this year, when we ship Windows Server 2016, Service Fabric will be built into that. You'll be able to build clusters from that, deploy your applications there. And we're excited to be able to say that we're entering a new era of how we think about how we build these high-scale, high-resilient, mission-critical services like we run at Microsoft. And we've given you exactly the same technology for you to do the same. And think about how we're going to take this into the journey of how we build true-scale, highly resilient services. So thank you very much. I think we have some time for some questions, so please come to the microphones or if you don't,
come up to the stage.
Or come up and ask on the stage. And we would love to hear questions at the microphones first if you want to go to those. Yes, is the microphone on? Can we turn the microphone on, please? Can we turn the microphone on?
For the question and answers, can we turn the microphone on, please?
Do the microphones work?
Should I just walk up?
Why don't you come up and then I'll repeat your question.
Okay, yes, ask the questions then, or shout them out and we'll repeat the questions. Okay, so good question. The question is what's the migration path from existing cloud services going towards this, and will we be continuing to invest in cloud services we have today? The answer to that is cloud services will continue, and we'll have that for many, many years as a programming model inside there. We'll provide migration guidance of moving forward to this. Effectively, you'll see today that the programming model API is very similar, so the migration pretty much is, there's a similar programming model, and we'll provide design guidance around all of those. Our investment in cloud services, you should think about this as the next generation of our PaaS platform. We've shipped this as a parallel service that you can use. We'll keep them both running side by side. But this is one where we now have fast deployments, high density, greater scale, and this is where we've invested our time. So cloud services will remain, but this is where our investment is going forward. This is your next version of our PaaS platform. This is exactly how we build things. Well, as I said, we'll run both sides. And you'll see today, we showed in the stateless world today, you build a cloud service, it's very similar. It's got the run command, it's almost identical you have today. We've just done a better separation of the runtime from the environment. So you can take those cloud services or those stateless applications now and run them anywhere. Today, cloud services are sort of constrained. They'll only run inside Azure. They're fixed there. You're locked in. Now you can run them on premise. You can stand up anywhere you want to run these things. So you have the benefit of run anywhere, fast deployment, high density. This is the next generation of that. So next question is how does it fit with Resource Manager? You'll see that we'll stand up a service later this year that has a Resource Manager definition of.
the next talk, and they'll talk about how
Oh,
to.
actually, that's even better. In the next talk that follows, we'll show you exactly how you stand up a cluster.
Okay.
We'll show you the portal, what it runs like, how you define a resource manager template. But yes, we'll have a template definition to be able to stand up a cluster of machines and deploy the applications.
We'll take one question here. Yeah. Yeah, so you can actually.
Just repeat the question.
So it's basically
Just
durably
repeat
saved.
the question.
Oh, so the question is, what happens if I actually shut down the entire cluster and then restart the entire cluster? Well, the data is durably stored on the disk, and hence, if you shut down the cluster, as long as your hard disks don't burn or they're still available, you will be able to recover from where you started from.
No, it's the
No,
physical
so
machine.
there is no blob storage backing. This is the store. Your local hard disk is the store. You can, however, for disaster recovery as well as, so for example, if a disaster were to happen and you say, hey, well, the entire rack got burned down and I didn't actually geolocate the data, you could store it to the blob store. But that is a different frequency. It's a cold data that's only for disaster recovery. It's not in your hot application path, and hence your latencies are not going to be affected by that.
Yeah, there's a general design that we've come across here where you hold hot data in a middle tier, made highly available and scalable, and that hot might be the last minute, the last hour, the last day, and then you can offload that data to back-end Azure storage. But as a result, you have this very low latency, high throughput systems you build. So for example, Cortana, think about it, hundreds and hundreds of requests coming per second, they have to evaluate them all. If they tried to build that with storage and put all those events there, they wouldn't be able to scale it at all. IoT is like the perfect example of this sort of system. IoT systems where you have huge amounts of incoming data, where you want to run rules on it all, that sort of thing. But SQL Azure builds like this, yeah? The database is stored on local disks inside the machines. That's how we do it. DocDB, they store it on local disks on the machines. Intune, event hubs as well. Event hubs, we take advantage of using the same mechanism. Yes. Next question.
Yeah, so I actually, while we were talking, I actually shut down the local cluster. There are no nodes, so I shut down all of the nodes. I'm going to restart it again while we take the next question. You can go back to the which display port? Yeah.
Okay, so the question is I have my Azure DB running, and I have a client connection to a particular primary that's running, yes? And so effectively, the client, when the client calls back in again, we have a naming service that does a re-resolution of where the current primary is, yes? So think of it, there's a service that runs just like DNS for the whole cluster. So when something fails over, every microservice has a unique name. We know this is moved from here to here. The client comes back in again. The naming service is like DNS for the cluster. It goes, oh, it's here. And so we redirect the client to where the new primary is. And all of that just happens transparently to you. Well, once you've established to a primary, it is a TCP connection, it's directly, yes? But if you lose that, it'll reestablish a connection again, yes? But then how it does that is it goes in and asks Service Fabric, where is the new primary? And we tell it where it is, and then it just reconnects to the new machine again. And that's what you saw wrapped up in the Programming Model API, is that service partition resolver, that automatic re-resolution, rediscovery for you in terms of where things are. So things move around the whole time, things fail, things die, it doesn't matter, we'll just find it for you. Well, we provide out-of-the-box communication protocols both on Web API and WCF. If you want to build your own one based on TCP, sockets, FTP, you don't care. You can just implement a small piece of iCommunication listener and plug in your own one. So we don't really go much into the we provide an out-of-the-box communication experience to talk to your microservice. But if you want to build your own way of talking to it, go ahead, it's free. Most of our benefit is the fact of dealing with failover, discovery, lifecycle management, and resilience and composition of a service into smaller pieces of code. Yes?
Yeah, the transaction model makes sense. Makes me wonder, what's the conflict model, and how soon will I run into performance issues when I make too big transactions, too much in
Do you want to take this question on? This is about transactions across the dictionary.
Yeah, so the logs that we take are timeout based, and so if you have a big thing inside your transaction, the other guy is going to time out and say, hey, I cannot acquire the log for this particular key. and they're key-based. So if they are not conflicting, both of them will go in parallel. And the transactions that you asked a different other question, which is what happens if I have a large set of items inside the transaction? What happens is that as you are making the changes, those are actually getting replicated at that point in time. So we're not waiting for the commit. We're assuming that most of the commits will successful, and hence we can actually replicate while you are doing it. And so as a result, we don't accumulate a large big chunk and then replicate in the end. It's actually replicating, and so you're not accumulating that.
However, you use set logs, so is it fair to say that it's more like log-based?
Yes. Yes.
So it's not like multi-version?
Well, for enumeration, it is multi-version. So it is both. For the enumeration, it is multi-version snapshot isolation.
Yeah.
Yeah, because if you only have repeatable reads, you'll get phantom reads in the when you do the enumeration. And in order to avoid that, we have multi-version for the enumeration.
Yes, on our docs online.
On our
if you look
docs.
at, yes, if you look at our docs online. Yes, let's take the next question. We've probably got time for a couple more.
No, it was all running on this machine.
Yeah.
And in fact, if you notice, I wasn't even connected anywhere on the wireless. And so you can actually, so in a production, that particular node will be one node on one machine. But you can actually configure to run multiple nodes within the same machine. In fact, in our test, we run hundreds of nodes, not only on same machine, but within the same process. And so we're able to do a lot of failovers and actually do white box testing to be able to figure out. So the code is exactly the same. There is no difference in terms of whether it is running on a single box with 10 nodes or whether it's running inside the Azure with one node and one in one box.
For those who saw Mark Brazonovich's demo yesterday, where it was voting app, we actually had hundreds of machines there running in the background. He didn't show the hundreds of machines, but we had hundreds of machines piling hundreds of votes into a set of services that we were running to show the big scale that he just deployed it on. And he just partitioned out the application across as many machines as your choice.
Right.
Yeah. So,
Yeah,
so, I
so,
mean, I'll let you go.
sorry. So what happens is that the cluster that Mark showed in one of the slides, that the nodes are forming the cluster. So let's say if you had one machine go down, we will detect that that machine is down, and the rest of the node will basically heal around it and form the cluster, and then fail over the workload that was on this machine to a different machine. In this case, the entire cluster went down. Because I had all the nodes in that cluster on the same machine.
In fact, in the talk that's happening next, we're going to show clusters running on Azure, and we're going to use that same testability service to actually show testability on clusters running in Azure, not just on your local machine.
Right.
So you'll see it there.
And if you notice, I think this is a little bit more deeper, but if you notice, I did something else as well before starting. I deleted what we call a ticket files. That's basically to prevent the split brain situation. So I knew that I had the entire cluster down. If I had only the portion of the cluster down or there was a network partition, there is a leasing duration for which we will wait before we will say, hey, those machines are dead, and those machines will actually go down. Those nodes will actually go down. So you will never have split brain situation in your cluster.
Yeah, the clustering technology is very important in building a platform. Yes, so the SDK is available. Everything you see runs on your local dev box, just as you can. And then what happens is you'll simply go up to Azure and say, create me a 10 machine VM cluster that's running there, and the apps will just deploy up there in exactly the same way you saw running here. The same WinFab Explorer, you can attach them all. It's no difference. Oh, you can do it on
you can run it on premise.
Yeah, we run it all on. We run it everywhere on premise.
So that's one follow-up question.
Yes.
So on-premises would be available?
Correct.
Yes.
So the question is it on-premise? Yes. You'll see in a few months' time, we'll ship a version of, you can create a cluster inside Azure of machines. It'll be shipped as part of Windows Server 2016. And so you'll be able to take Windows Server, you'll be able to network them all together, turn on Service Fabric on each one, have your cluster. Anywhere you have network connectivity, you can build a cluster of machines effectively. Next question, yes. This technology, yes.
So there are multiple layers of the APIs. We talked.
Okay.
Okay, so why don't we go out and take the question?
Okay.